In this next module, we're going to talk about the concept of expected value, which is just a fancy word for mean, which is a concept we've already talked about in this course. But expected value is a really great tool for making good decisions. So we're going to spend a lot of time on expected value. So what is expected value? Again, it's just the mean. It's the mean of a probability distribution. And the way that we calculate this mean is slightly different than the way that we calculated a mean when we had data. So when we have data, we calculated the mean by adding up everybody's values and dividing by n. That doesn't quite work when we have a probability distribution, because for a probability distribution, certain outcomes occur more frequently than other outcomes, and we have to factor that in. So what we're doing is we're actually weighting the value of each outcome by its probability. So it's a weighted average. That's a little bit different than how we calculate a mean for sample data, where everybody occurs equally frequently. And again, expected value is just this great concept. I love to talk about expected value because it helps us to make informed decisions. And the idea is that we're talking about, on average, what do we expect to happen in the long run? And so this gets back to this frequentist view of probability. We're saying in the long run, what value do we think will occur? So kind of put that in the back of your mind. We're talking about if you could repeat things over and over again, how often will different outcomes occur? It's a frequentist view. So expected value, to calculate it, all we're going to do is we need the probability distribution. Once we have that, we're going to take each value of x, each possible outcome, we're going to take its value, and we're going to multiply it by its probability, how frequently it occurs. So outcomes that occur more frequently will be weighted higher in this sum. We're going to take those weighted values, and then we're going to add them all up. So this is just saying add up all the x's times their probability, all the possible outcomes times their probability. I'm going to show you some examples of how to calculate that. Now I just want to show you, I'm not going to spend too much time on the continuous case because it's really beyond the scope of this course, but I'm just going to show you how this extends to the continuous case. So in the discrete case, we're adding things up, so it's a summation sign. When you move to the continuous case, when you have an infinite number of possible things to add up, instead of summing, you're integrating. So that's the analogy. The analogy in the continuous case is the summation sign becomes an integral. But notice it's otherwise exactly the same. We're going to integrate over all possible values of x. We're going to take x and weight it by its probability. But since there's an infinite number of possible x's, we have to do an integral here rather than just adding up discrete values. Again, we're not going to talk too much about the continuous case, so don't get thrown by the integral, but just to give you a sense that it extends to the continuous case. It's very easy to calculate expected value for the discrete case. So recall we had this probability distribution about how many patients were arriving in the emergency room in a given hour. And let's say, it's an artificial distribution, but let's say this was the actual distribution. What is the expected value or mean number of patients in any given hour? On average, how many patients are we expecting to see per hour? That's an important piece of information for determining resources for the emergency room. So just as when we talked about the sample mean, you can think about the expected value as a balancing point. If each of those numbers, 0.3, 0.3, 0.2, those represent masses on a fulcrum, on a lever, the mean is the point where you have to put the fulcrum to balance those masses. It's the same concept. Now, students tend to be tempted, if I tell students to calculate the mean here, their first instinct is to just add up the 5 numbers and divide by 5, right? You're tempted to just go, oh, I have to calculate a mean, so it's 9 plus 10 plus 11 plus 12 plus 13, add those up, divide by 5. That's how you've always calculated a mean all your life. But that's not going to be quite right here, because 9 occurs more frequently than 13. So we have to weight 9 by the fact that it occurs more frequently. So to calculate the expected value, what we're going to do is take the value of each x, so of each outcome, and multiply it by its probability. So 9 times 0.3. And then we're going to add that to each other outcome. So we're going to do 9 times 0.3 plus 10 times 0.3 plus 11 times 0.2 plus 12 times 0.1 plus 13 times 0.1. When you add all that out, sum it all up, it comes out to be 10.4. On average, we're seeing 10.4 people in the emergency room in any given hour. So you got to remember when you're calculating these that you have to weight them because the outcomes don't occur equally frequently. Now, a sample mean is actually just a special case of expected value. So remember in the first week of the course, when we calculated the sample mean, what we did was to add up the values for everybody in our sample and divide by n. That's something you've been doing all your life. Well, if I've just rearranged the summation a little bit here, I can show you that that's the same as taking every person's value and multiplying it by 1 over n and then adding those up. So every person is being weighted by 1 over m. That's their probability, that's their frequency in the sample. It just happens that everybody counts once, so everybody has the same weight, so we don't actually have to multiply everybody by the weight, we can just divide by n at the end. But really that's everybody's weight. Everybody has a probability in the sample, frequency in the sample of 1 over n. So this sample mean is really just a special case of expected value. I want to just make sure we're keeping our symbol straight here. So when I talk about sample means, I use the symbol x bar. That means we calculated the mean from sample data. When I'm talking about calculating means from probability distributions, which are theoretical things rather than from data, I'm either going to use the symbol mu, which is a Greek letter, or I will interchangeably use E of x, which just stands for expected value of x. Remember, the mean and the expected value of x are the same thing. It turns out to be easier on a typewriter sometimes to write E of x rather than to find the Greek symbol mu. So you'll see a lot of times I'll just use EX instead because it's easier on my typewriter. But those mean the same thing.